Okay, let's begin. So, what does the first one look like? What's the picture? Jumping right into it. So if we have f of x equals x squared minus 4 over x minus 2, what does that look like? Yeah?
It's a linear line with x-intercept at plus, or y-intercept at plus 2 and a whole at.
How did you get that?
So you factor the x squared minus 4, so it's x plus 2x minus 2.
So this, you realize that x minus 2, x plus 2, because we're all great at algebra and we recognize the difference of squares here. So that simplifies to x plus 2, which is a straight line with slope 1 passing through y-intercept 2. But is it exactly that? Like, is this exactly that? Is there no difference between these two? Like, what's an issue that this one has? Yeah?
There should be a whole at x equals plus 2.
Right, like you can't be 2. So this is not just a real, like, everyday x plus 2. It's an x plus 2 where you're not allowed to plug in 2, right? That is because of something that students often forget. Simplifying does not fix your domain. Like 2 couldn't work in the beginning, it's not going to work after you simplify, right? Simplifying just helps you figure out the pattern, which here, clearly you know is just a straight line with positive slope. The difference is it cannot work at 2, so how you deal with that is at 2, you realize that there is what we call a hole. And yes, that is a technical term, that's actually what it's called. You look at it in a textbook, it's called a hole. One thing you realize with math people, we're horrible at naming things, not very creative. Oh, it looks like there's a hole there, let's call it a hole. Like, definition, a hole is, right, so when the function doesn't exist at an isolated point, we call that a hole. So there's a hole there, but that's what the picture looks like. It's a straight line, except for at 2. You can't put in 2, but otherwise, this is just a fraction that we can reduce and simplify to x plus 2. Now we play our game from before, because I'm inching closer and closer to 2 here. I'm on the graph, so I'm inching closer and closer to a location whose y value is going to be something like that, and I'm inching closer and closer to 2, and I'm inching closer and closer, and I kind of end up with the same thing. And what is this location? What's the y value of that hole?
Undefined.
Yeah, well, if it were there, like this location, what's the y value of that?
4.
It's 4. So if we could get there, the answer would have been 4. And so we can say that the limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. Now remember, the limit doesn't actually care about the fact that we can't actually be there. The limit just cares about what is the y value getting close to as we move towards there. Now since this behaves pretty much like x plus 2 all the way through except at that one point, x plus 2 would have passed through the value 4 here. It's just that we don't. But the limit actually doesn't care. The limit is going to give us the answer 4. What about the next example, f? What does that look like? Or do you sketch that one? Yeah?
A horizontal line from 1 to infinity, where x is equal to 1, I mean, to where y is equal to 1, and it's an open circle for the first part.
Where does the open circle happen?
For where x is equal to 1 towards infinity, because oh wait, never mind, I'm lying. It's when it's less than 1.
Okay, so there's an open circle
Yes.
here, because we are less than, and it's just a horizontal line.
Yes.
Y equals 1, going off to negative infinity. What about on the other side?
Then you have a closed or like shaded circle on 1. And then it goes, I think.
Like that?
Yeah, I think so.
How does it look? What is x minus 1 squared?
Squared, well, it's,
Yeah?
It's a quadratic.
So it's a parabola,
Yeah.
and it's opening upwards, so it's kind of
like a
curved off like that. So that's the picture. And of course, what you want to realize is that with piecewise functions, you kind of graph them in pieces based on where these things should work. So you notice here it's broken up around 1. So if it helps you, what you can do is you can graph both separately. Okay, so I know that y equals 1 would look like that. But I only care about what's on the left side because I have to be less than 1. So you kind of ignore this part. And if we're graphing y equals x minus 1 squared, well, that's just like y equals x squared, but it's shifted 1 unit to the right, so it'll look like that. Because we want to be greater than or equal to 1, we ignore that side. And so to graph the piecewise function, what you realize is that since it's broken up around 1, there's this like invisible barrier here. And you kind of know that, okay, on the left side, I'm going to draw that picture, and on the right side, I'm going to draw that picture. Kind of morph the both pictures into one. We are less than 1, so we can't exist here. We can be equal to 1, so we are filled in there. Now that we have that picture, what is the limit? Does not exist. Why?
Because it's not the same from both directions. I might be wrong.
Okay, so we're playing the same, let's play the same game we played over here. Okay, so I'm getting closer and closer and closer to 1. What is the y value of the location I'm heading towards? Well, it's 0. If on the other side, if I'm getting closer and closer and closer to 1, then that means I'm on this graph over here, because that graph doesn't exist. And the y value of that location is 1. And those don't agree. There's ambiguity. So it violates our definition. Does not exist is the answer. Now, yes?
How would you, in like a notation form, put like coming from each side, if that makes sense? Like, could you ask us like if it's coming from one side versus the other, and like?
I could.
Okay.
We'll get there, but the
Okay.
limit overall does not exist because of that. Okay? Now, the point of this example is one thing I just want to make clear, because some students in my earlier class made this mistake. They thought the answer was 0 because it's filled in here. But I want you to remember, limits don't care about being filled in. We don't care about actually getting to the point. We care about what's happening as we get close to the point. What's happening to the y value as we get close. Now, as we get close to 1, there's disagreement in what the y value is doing. Sometimes it's going to 0, sometimes it's going to 1. But yeah, so the limit overall does not exist. That would be the answer. Because there is no unique y value that we're approaching as our x value approaches 1. But yes, as was mentioned, because that's not really satisfactory to say. Like, I mean, if you think about why we even invented the concept of a limit, it's because we kind of wanted to examine functions in a way, one of the main reasons, we want to examine functions where at a certain point we really care about what's going on at that point, but something crazy happens at that point and we can't really be there. So what we do is we use a limit to say, okay, as we get close to the point, what is going on with our function in a neighborhood of the point? So can we kind of figure out how to deal with that point by realizing what's going on close to it, right? So in this situation, you'd realize the limit doesn't exist, but it's not because we don't have any idea what's going on. We can clearly see what's going on. If I'm on the right side, the y values are going to 0. If I'm on the left side, it's going to 1. So this example, so there's the notion of what's called a one-sided limit. So sometimes overall the limit does not exist, but we do actually know about what the y value is doing if we look at it one side at a time. And in that situation, one-sided limits are going to be important. The notation, as was asked, is the following. So if I have f of x approaching a, and what I do is I put a little plus sign in the superscript here, so it's in the power to the top right corner of the a. That is what we call the limit as x approaches a from the right of x. Okay. So that's from the right. Okay? So that means we're not at a, we're a plus a little bit, right? So it's 1 plus a little bit, right? So we're on the right side approaching a, right? So this is when your x is slightly larger than a. And it's approaching it. Okay. We can use this notation to represent the limit as we're looking at that one side. We can also use the limit as x approaches a, and we put a little negative sign here, a minus sign. Fx. This is the limit as x approaches a. From the left. And this idea about coming from the left. So this means your x is slightly smaller than a. And it's approaching a. So you're 1 minus a little bit, right? So on the left side, right? And we can talk about that. So in the above, which now is to the right, technically. In your notes, it's probably above. If I look at the limit as x approaches 1 from the right of our function, and the limit as x approaches 1 from the left of our function, these will actually give us values individually. What is that?
0,
This is 0.
1.
That's 1. So I do know about how the y value is behaving, just one side at a time. But because these two don't agree, the overall limit does not exist. And that is cause for another definition / convention. So the limit as x approaches a of f of x, no, that's not really a definition, only exists if both one-sided limits exist, both the limit as x approaches a from the left of f of x and the limit as x approaches a from the right of f of x exists, and they are equal, then the limit as x approaches a of f of x is their common value. And if you look back at your notes, you'll notice that we've kind of been playing this game the whole time. We always look at inching from both sides, right? I drew those arrows approaching from both sides. And so we often want to look at both sides. Sometimes the function itself at the point is kind of weird, so you look at one side at a time. And if you can determine one-sided limits at a time, you can determine the overall limit by just seeing do they agree or not. It is, of course, possible for either of these guys to not exist, and then the overall limit won't exist. But if they exist and they're equal, the overall limit exists. That's the notion of a one-sided limit, which we will be using from time to time. Let's do some more remarks. There are some nuances with limits that you can get in trouble with, so let's just actually mention those. More remarks. One, f of x need not be defined at x equals a for the limit to exist there. Again, we don't care about whether the values of the function it exists there, or if it lives there, or if it's filled in or not. You don't care about being at the point, you care about being close to the point. The limit x approaches a of f of x cares about what the y equals f of x gets close to. Let me the phrase is often arbitrarily close to, as x gets arbitrarily close. Arbitrarily. So as your x is getting arbitrarily close to a, you want to know what is the y value getting arbitrarily close to. Arbitrarily close means, that's also a technical term. Basically what that means is essentially as close as you want is the idea. But it means we can get closer than any given positive distance. So that's automatically important. So for example, here's a function 1, there's a hole there, bless you.
Thank you.
Right? Now the function doesn't exist at 1, but the x values we can get arbitrarily close to 1, right? The function exists as close to that point as I want it to exist. And so the limit will work out in that situation. A situation where a limit would not work out, it won't even make sense to even talk about a limit, is let's say you're at 1 and you're a point here, but now beside that there's like a gap. And beside that there's a gap, and the function is doing whatever. And this is at say a half, and this is at say 2, and so here we cannot get arbitrarily close. here we can get arbitrarily close. Here we cannot get arbitrarily close. And arbitrarily close basically means we can get to within whatever positive distance someone mentions. Here you'll notice if someone says, can we get within a quarter of a unit close to 1? The answer would be no. Right? Like, I can't actually travel to within a quarter of a distance from 1. The function doesn't exist there. There's a distance of a half between 1 and the next point that I can even remotely touch. Right? Similarly here, there's a distance of 1. I can't get arbitrarily close to 1. The limit as x approaches 1 of this automatically does not exist. I'm unable to get close to it. Now, yes, it's filled in. We don't care. The limit does not care about being filled in. The limit cares about what are we getting close to. So I can't get close to 1 because someone can ask me a positive distance and I can't get within that distance. Right? So I have to be able to get as close as I want to the point without ever actually being at the point itself. Right? So that's a very important idea with limits. Now, something magical happens when we can actually get close to the point and at the same time it's filled in. And we'll talk about this a little more later, but I'll just introduce the idea now because I want to mention it in a bit. If the limit exists and at the same time it happens to be the value of the function at a, meaning it's a filled in point. So I can get arbitrarily close to it and at the same time it's filled in as the same number. Then f of x is called continuous. At x equals a. We'll talk more about that later, but that's kind of like when you can approach a point and at the same time it's filled in as the same point. Right? So this is continuous at x equals 1. And continuity is important because calculus only works where we're continuous, right? If a function doesn't behave that way, we can't actually do calculus. What else do I want to mention? Some terminologies maybe. In the limit as x approaches a of f of x equals L, if our L is infinite, which we've seen examples of that, then the limit is called an infinite limit. So example, we had the limit as x approaches 0 of 1 over x squared. The answer is infinity. That's an infinite limit. If the a value is infinite, plus or minus infinity, then it is called a limit at infinity. Okay, so for example, the limit as x approaches infinity of 1 over x was 0. And we call that a limit at infinity, where the input values are going to infinity. We say at infinity, we're taking a limit. You should notice that a limit may be both. So for example, if I look at the limit as x approaches infinity of x squared, the answer is going to be infinity. That's an infinite limit at infinity. Some terminology. Taking a limit at infinity means the x is approaching infinity. If the answer is infinity, we call that a limit, an infinite limit. Questions? That's just some terminology here. I think those are all the remarks I want to make at this point. So what we're going to do now is learn how to compute limits. We're going to talk about computing limits. And we'll spend the next couple classes on this. So, yes, we were finding limits the whole time, but we're more doing it by feel and intuitive sense. We're drawing pictures and stuff. But how do I actually go about calculating something quickly, computationally, where I don't have to draw the graph, and I can actually start finding limits quicker, right? Only draw a graph if I have to, right? So there is a certain strategy that you want to employ that I'm going to tell you guys about now. Because on your next quiz, I'm going to ask you a question where I'm going to just give you a bunch of limits. I'm going to say, compute all these limits. I'm not going to tell you how to approach it, what to do. You just have to look at it, figure out how to approach it, and then get to the answer, the correct answer. Okay? So here's the strategy. You want to find a limit. So when faced with, right, so this random limit pops up on your test or whatever, on a quiz, a test, this random limit, okay? It might look very scary, right? Step one. First thing you're going to try to do when you see any limit, try to plug in. Because if your f is continuous, and by the way, in this class, most of the time I'm going to tell you something that are continuous. Continuous functions are going to be all the guys you've pretty much seen before. Polynomials, exponentials, logs, trig functions, rational functions, radical functions. These guys are all continuous on their domain. So once you can plug in an x, it will be the case that you can arbitrarily closely approach that x. Just that the nature of the functions we'll tend to look at will have that. If f is continuous, then remember that the limit is going to be just plug in the value, plug in a into the function. Right? So try to plug in a. We did an example like this. Our first example was one simple enough to do this. We asked about the limit as x approaches 1 of 3 minus x. 3 minus x, that's a polynomial, it's a pretty nice thing. We can get close to 1 without issue, and we can actually get to 1 and fill in the value. So I see that. I'm just going to plug in 3 minus 1, 2. Choose the answer. Didn't have to graph it or anything. Very nice function. Can plug in, get an answer. Right? There are no isolated points, so there was no gaps to worry about like we had, like I drew over here. So you can just plug it in. So it's the first thing you're going to do. Now that looks very simple, but the function could look very complicated here. Don't be scared. First thing you try to do, you see a limit, try to plug in the number. If it's possible, you can actually calculate something, that's your answer. Okay? Now that doesn't always work, of course. So step 2. So let's say you can't plug in the number. Here's the next thing you try. Try to simplify so that you can plug in the number. Our first example today was something like that. So here, let's say I have the limit of x plus 2 of x squared minus 4 over x minus 2. First thing I try to do, plug in x minus 2, x equals 2. Can't do that because I would divide by 0, and then Jhevon's going to kill me. So, can't plug in x equals 2. So step 1, can't work. Move on to step 2. Can I simplify this to a point where I can plug in 2? And the answer would be yes. So earlier we saw that we can factor that into the difference of squares. And so it's like that. It behaves like x plus 2, arbitrarily close to 2. Now it doesn't actually exist at 2, but the limit doesn't care about existing at 2. It just cares about what it's behaving like very, very close to 2. And if it behaves like x plus 2, then as x approaches 2, it's going to behave like 2 plus 2. I'll plug in. And the answer is going to be 4. So if I ask you that limit, you will write this down. That's the answer. The answer is 4. One thing I want to note here about notation. Note writing the limit part until we actually take the limit. So notice here that I kept writing down this limit thing, right? So while I'm simplifying, while I'm breaking it down to get into a more convenient form, I keep writing the limit because I'm not taking the limit yet. At this point, I'm at a point where, yeah, I can just plug in and get the answer. So once I plug in, I drop the limit sign. So I drop the limit sign once I plug in. So no limit sign. Plugging in. So once I can get to a point where I can plug in or determine, say, the limit does not exist or something like that, I stop writing that symbol. But until then, I keep writing them. Yeah.
Can you just keep writing it or no?
Well, no. So you don't want to write it here. So your final answer should be a number, or does not exist, or plus or minus infinity. Yeah.
And if we forgot to put the limit, we have points taken off?
Yes. I'll take off the point. So keep writing it until you get to a point, okay, I can plug in, or I know what the answer is. Did you? Okay. She's stretching. Let's, so those are the first two things you'll do with approaching any limit. Now the third thing that you're going to do, because there are times when that won't work, step 3. Now step 3 would be to try to apply special technique. We'll come back to this. So, I think, well, in the main Cal 1 class, I tell you guys a bunch of special techniques, but in 1203, I'll probably actually only tell you like one of them. Because the other ones will work with trig functions and stuff, and we're not doing trig in this class. So, so we'll come back to that. So step 4, or step 5. I'm going to give you another step, which is kind of interchangeable with this one, is to, I would say, use the graph or table of values. So, say, example, limit as x approaches 0 of 1 over x, right? Now you look at that, let's say 1 over x squared. Now you look at that and you realize, can I plug in 0? No, do that, Jhevon's going to kill me. Okay. Can I simplify so that I can plug in 0? Well, no. There's nothing that's going to cancel those two x's in the bottom, right? So I can't do step 2, I can't simplify, right? Don't know about special techniques here, we'll get to those. But in step 4, I do know what the graph looks like. So one way I can figure this out is to actually do the graph. So I know that the graph looks like this. So if it's easy, something that's easy to graph, I'll probably just do a quick sketch. And both sides, from the right it's going up, from the left it's going up. So this means the limit is infinity, right? Or let's say it's complicated, you don't know the graph, or you don't want to have to draw the graph. You could do a table of values. And here's how that would actually look. So, or your table values. So x, y, your y is now 1 over x squared. And just going to do a table of values. Now, how big this table is, it's some part is partly intuition. You want to just see if you can actually see a pattern after a while. But you care about x being 0, and you don't know what the y is doing at this point. What you can do is you can inch close to 0, and I mean arbitrarily close to 0, very, very close. So I'm going to start plugging in values that are getting closer and closer to 0. You want to start very close. Like, I'm not going to start at 1. That's like forever away. So let's start like 0.1, 0.01, 0.001, 0.0001, etc. Right? So I'm inching my way closer and closer to 0. And of course I can do this from the negative side, 0.0001, 0.001, 0.01. That's 0.1, etc. Right? Now, I'm going to pick some nice numbers that I can actually plug in, but they're very small. 0.1 is 1 over 10. If I take the reciprocal and square it, that's going to give me 100. This is 1 over 100, take that reciprocal and square it, that's going to give me like 10,000. Take this reciprocal and square it, that's going to give me like 1,000,000. Take this reciprocal and square it, that's going to give me like a lot. Right? So notice what's happening with our y values. There's a pattern that I'm picking up on. The pattern is they just keep getting bigger. Right? And you can see that the closer I get to 0, the bigger they'll get. So this is going off to infinity. In this situation, pretty much the same thing is happening, and it's squared, so it's actually turning all of these guys positive. You're having the same, try counting these zeros. You're having the same idea. This pattern is also going off to infinity. And so where do we expect them to meet? Well, at infinity. So, and I'm going to guess that the limit as x approaches 0 of 1 over x squared is infinity. So forget the graph, you can just plug in numbers, inch your way close to 0. See, is there a pattern that I can take advantage of? Here I can see, oh, they just keep getting bigger. Notice that in the case of 1 over x, these guys would all get bigger, but because of the negatives, 1 over x will give you negative signs coming all the way up here. So this side will go to negative infinity, that side will go to positive infinity, and then does not exist. But in this case, they both kind of match up. So that's how table of values would work. One way to express this, by the way, is you can use charged zeros. So one way to kind of explain what's going on with this guy is that your denominator is going to 0. Now you'll never actually make it to 0, but it will always give you a positive number. One way you can write it as 0 with a little plus charge. Right? So it's a little charged 0 here. Now, this is of course something you have to be careful with because you forget that plus, Jhevon kills you, right? So here, this means slightly positive, but very close to 0. So you never write a 0 in the denominator unless you're indicating that it's signed somehow, meaning it's not really 0, it's 0.000 something, right? But it's slightly charged, and so if your numerator is not 0, and your denominator is getting closer to 0, it's going to blow up to infinity. And so here you just take the charge with it. So how you can do this, let's say a slightly more complicated problem, how you could actually write this out. Let's say I asked you, what is the limit as x approaches 1 from the right of x squared minus 4 over x minus 1? So you look at that, right? Random limit shows up on the quiz. First step, try to plug in. Can I plug in 1? No. If I plug in 1, I divide by 0, Jhevon goes. Okay. 2, simplify the plugging. Can I simplify? Well, I realize that there's a difference of squares here. So it's x minus 2, x plus 2 over x minus 1. I still write the limit, and I'm trying to simplify it. Damn it, nothing cancels. Okay, so I can't simplify to be able to plug in 1. So now what do I want to do? Graph that? No, I don't want to graph that. That's going to take forever. Table of values? That's also going to be kind of annoying. But I can start to do something that's almost like a table of values. I can start to plug in. Now, the problem is the denominator. But in the top, as x is going close to 1, this factor here is getting close to minus 1. this factor here is getting close to 3. The denominator is getting close to 0, but it's not quite 0. It's 0 with a positive charge. How do I know it's 0 with a positive charge? Because it's 1 from the right, which means I'm slightly bigger than 1, right? So my x is something that's slightly bigger than 1. So if I take something that's bigger than 1 and subtract 1, I get a positive number. So I'm approaching 0, but it's a slight positive charge. So now what you'll notice here, numerator not 0. 0 divided by 0 is a whole other ballgame. So let me make sure that you realize that the numerator is not 0. Okay? But denominator approaches 0. And it's positively charged. Right? So what that means is, if your numerator is not 0 but your denominator is approaching 0, it means it's going to blow up. Whenever you divide a fraction by a smaller denominator, it gets bigger. So the answer is definitely going to be infinite here. But if you try to determine which infinity, now you have to take the signs into account. Notice that this is a negative sign in the numerator, and there's a positive sign in the denominator. So the numerator is a negative number, the denominator is a positive number, so negative infinity is going to be the answer here. Okay. So I ask you that limit, the answer is negative infinity. Right? And I kind of go through the strategy, try to plug in, oh, can I do that? Can I simplify? It doesn't work. All right, if I inch close to 0 by plugging in numbers, what's going to happen? Well, top is negative, denominator is a slight positive charge. So denominator is approaching 0, you can't stop it, right? Because you would have tried to stop it in step 2. So whenever your denominator is approaching 0, the numerator is not 0, it's going to start blowing up. You just want to know, is it blowing up to positive infinity or negative infinity? And at this point, you just watch the signs that are involved. If we look at the last way, so this is step 5 and or step 4. Depends on what you see first. Is use your knowledge. I have knowledge of the behavior of functions. So I mentioned some of these to you before, but let me expand that list a bit. So we do know that logarithms grow a lot slower than polynomials, and those grow a lot slower than exponentials, and those grow a lot slower than... You'll probably never see this. If you do Calc 2, you'll see it. If you do probability, you'll see it, but we're not really going to do this function, so don't worry about it too much. It's called a factorial. Right, so this is the list as x goes off to infinity. Now remember what this symbol means? It means the guy on the right is so much bigger than the guy on the left that the guy on the left might as well not even try. He's going to be very small compared to the guy on the right. So small he might as well be 0 or very close to it. So knowing that, if I saw a problem like this, looking at that, right? Notice here that the numerator is a polynomial, but the denominator is an exponential. So what that means as we're going off to infinity, the denominator is going to be huge compared to the numerator. So the numerator, this is approaching something very small. The denominator is huge, right? Now how does a fraction behave if the denominator is huge and the top is small? Well, it goes to 0. Right? So I can just look at that, the answer is 0. Right? But I really went through a bunch of things in my head, but can't plug in infinity, that's not a number. Can't simplify that, don't want to do a table of values, I have no idea what the graph looks like. But I know about functions. Polynomial, exponential is going to win as we're going off to infinity. Denominator is huge, so I'd say equal to 0. And as far as showing your work is concerned, for something like this, I'd probably say something like, which I'll talk about more next time, call it bottom heavy. Right? So the denominator of the fraction is much bigger than the numerator, it's bottom heavy. Whenever a fraction is bottom heavy, it goes off to zero. So, I'll have you guys do a bunch of examples for next time, but we'll stop there. That's the main strategy for approaching limits. We'll do some special techniques next time as well. We'll stop there. I'll see you guys on Friday.
Thank you.